An earthquake can cross an ocean without making a sound that human ears can hear. Long before anyone at a distant city feels a tremor, the ground may already be carrying a message. The entire field of instrumental seismology began with one stubborn question: how do you make the earth write that message down? A seismoscope only tells you that shaking happened, and sometimes its direction. A seismometer senses the motion. A seismograph is the complete recording system, while the line it produces is a seismogram. Those distinctions matter because detecting a shock is not the same achievement as preserving a usable measurement. The basic trick is inertia. A suspended mass resists sudden movement while the instrument's frame moves with the ground. The relative motion between them can drive a pen, a light beam, or an electrical sensor. The machine is not staying perfectly still. It is creating a reference stable enough to expose motion that would otherwise vanish. Recording the wiggle is only the beginning. The trace needs time marks because different seismic waves arrive at different moments. It also needs controlled friction, useful magnification, and a surface that moves steadily. A beautiful line with a bad clock is scientific calligraphy, not reliable evidence. One station can show that the ground moved. Several stations can compare arrival times, estimate where an earthquake began, and distinguish a local jolt from a distant event. The field, therefore, rewards more than a clever instrument. It rewards instruments that can be reproduced, maintained, synchronized, and connected into a working network. That network does more than catalog disasters. Seismic waves bend, reflect, and change speed as they cross different materials inside the planet. Comparing records from many directions lets researchers infer an interior they cannot drill into. Earthquake recording became a way to study both sudden danger and the hidden architecture of the Earth. Early pioneers faced awkward machinery, smoky paper, fragile clocks, damp rooms, and signals so small that ordinary vibration could bury them. A passing cart, a door slam, or a careless operator might imitate the planet. Reliability mattered because nobody could repeat the same earthquake on demand. So the GOAT in this narrow field must do 5 things unusually well: catch meaningful ground motion, preserve it continuously, make distant events comparable, survive outside one inventor's laboratory, and create a system that other people can use. A brilliant device alone is not enough. The winning contribution must turn isolated observations into cumulative science. The oldest serious contender appears in China in the 2nd century. Zhang Heng's bronze vessel reportedly used internal motion to release a ball from one of 8 dragon heads, indicating the direction of a distant disturbance. It was an extraordinary leap. An earthquake could be detected even when people near the instrument had not recognized it. But Zhang's machine was a detector, not a recorder. It did not draw ground motion against time, preserve wave shape, or let later researchers compare amplitude and arrival phases. Its conceptual importance is immense, yet the evidence it left was a direction and an event, not a reusable seismic history. 19th century Italy brought the problem into an observatory. Luigi Palmieri worked on Vesuvius, where earthquakes, volcanic tremor, and eruption signals were not abstract curiosities. His electromagnetic seismograph could register characteristics such as the time, strength, and duration of motion, helping turn volcanic surveillance into continuous instrumental work. Palmieri deserves credit for joining sensing, timing, and recording in a place where the information mattered immediately. Yet his achievement remains strongly tied to a complex local observatory and the special demands of a volcano. It advanced the instrument, but it did not yet make distant earthquakes part of one comparable worldwide record. In Japan, James Alfred Ewing attacked the mechanical problem directly. His horizontal pendulum design let a mass respond to sideways ground motion while a recording surface moved beneath it. After the destructive earthquake of 1880 near Tokyo and Yokohama, Ewing and his colleagues helped establish a new standard. Earthquakes should leave continuous traces, not merely trigger alarms. Ewing's work was foundational, and the early Japanese breakthrough was genuinely collective. Thomas Gray, Japanese officials, instrument makers, and other researchers all mattered. Ewing's strongest claim is elegant mechanical recording. His weaker claim is institutional reach. He did not become the person who bound many distant stations into a durable reporting system. Fusakichi Omori widened the field from machines to patterns. He is remembered for the empirical rule describing how aftershocks usually become less frequent with time after a major earthquake. That gave seismology a practical way to describe a sequence, rather than treating every shock as an unrelated surprise. Omori also designed instruments. His horizontal pendulum systems used smoked paper, and a later Bosch Omori form became affordable, viable, and common at stations around the world. He combined scientific interpretation with equipment that working observatories could actually operate, a much harder achievement than producing a delicate laboratory showpiece. That makes Omori a formidable contender, especially because his influence reached earthquake engineering, aftershock study, and international observatories. Still, his instruments entered a global culture of exchange that was already forming. His legacy enriched that system more than it originated the complete chain from standard instrument to centralized world bulletin. Then comes Emil Wiechert, the strongest rival. At Göttingen, he occupied the world's first university chair, devoted to geophysics, and built massive mechanical seismographs around the turn of the 20th century. Their large masses and strong damping produced dependable records, and versions of the design spread to major observatories. Wiechert's instruments were not portable ornaments. Some used masses measured in hundreds or thousands of kilograms, trading convenience for stability and sensitivity. They helped observatories separate primary waves, shoved waves, and slower surface waves, the distinct arrivals that turn a single trace into a journey through the planet. He also connected instrumentation to theory. Wiechert worked on the Earth's layered interior and supplied mathematical tools for interpreting travel times. In the history of heavy, high-quality mechanical seismographs, he may be the most impressive builder. He did not merely catch earthquakes, he made their wave trains scientifically legible. But the very strength of the Wiechert approach exposes its limit in this comparison. A superb instrument in a major observatory is still one node. The field's decisive transformation required many stations, computer procedures, regular exchange, and a center capable of converting scattered paper records into a continuing global account. The GOAT is John Milne. His victory is not based on inventing every mechanism or producing the heaviest instrument. It rests on something broader and harder. He helped turn earthquake recording into an international system whose instruments, observers, records, and publications reinforced one another. Milne arrived in Japan in 1876 as a young mining engineer and geologist. The Tokyo-Yokohama earthquake of 1880 pulled him deeply into seismology. With Ewing, Gray, Japanese scholars, officials, and technicians, he helped form the Seismological Society of Japan, the first society devoted to the subject. This was never a lone genius story. Ewing had crucial designs. Gray contributed instrumentation. Japanese institutions supplied knowledge, access, labor, and continuity. Milne's distinctive strength was synthesis. He kept pushing toward an instrument that could record ground motion against time, and then toward procedures that made records from different places worth comparing. The horizontal pendulum became central to that effort. By arranging the mass to respond to sideways motion and using photographic or mechanical recording, Milne's designs could register earthquakes too distant to be felt locally. The important advance was not simply sensitivity. It was sensitivity packaged in a form that could be reproduced and sent elsewhere. In 1895, a fire destroyed Milne's home and observatory in Japan, taking instruments and irreplaceable work with it. He returned to Britain and settled at Scheid on the Isle of Wight. The disaster could have ended the project. Instead, it forced the next and most consequential version of it. At Scheid, Milne built an observatory and made it the center of an expanding network. The underlying ground was suitable, but the real foundation was organizational. He persuaded scientific bodies and station operators to install comparable instruments, maintain them, time them, and send their observations back for analysis. The same horizontal pendulum pattern went to stations across the British Empire and beyond. Standardization was imperfect, yet it reduced one of the field's worst problems. Every observatory speaking a different mechanical language, a weaker instrument used consistently across many sites, could reveal more globally than one magnificent machine standing alone. Stations reported arrival times and copied traces. At Scheid, those fragments could be checked against one another. A disturbance recorded in several countries became one earthquake, with a developing geographic identity, rather than several mysterious local wiggles. The network made distance itself useful evidence. Milne's Scheid circulars published the combined observations. That sounds bureaucratic, which is precisely why it mattered. Science advances when results survive the inventor, reach strangers, and can be corrected by later work. The circulars became ancestors of the International Seismological Summary, and, Detwally, the bulletin produced by the International Seismological Center. The network was also a social machine. Professional observatories, colonial stations, amateurs, assistants, instrument makers, and clerks all contributed. Shinobu Hirota, Milne's long-serving assistant, was essential to maintaining instruments and processing records. The GOAT label belongs to Milne's coordinating achievement, not to a fantasy that he worked alone. Weichert remains the hardest challenge. His heavy seismographs were often more powerful, and his theoretical work penetrated deeper into wave behavior and the Earth's interior. If the field were the greatest mechanical seismograph builder, Weichert might win. In foundational global instrumental seismology, Milne's network and publication chain carry greater weight. Milne's system had real limits. Its instruments were surpassed, station quality varied, and the network leaned heavily on imperial roots and unequal institutions. His achievements also depended on collaborators whose names are less famous. Those qualifications do not weaken the conclusion. They define it accurately. His greatness was architectural rather than solitary. Modern seismology uses electronic sensors, digital clocks, satellites, and near-instant data exchange, but the governing idea is recognizable. Comparable stations report into a shared international record. John Milne deserves the title because he made the earthquake larger than any one observatory. He showed that the Earth could write globally, provided people agreed how to read the same page.